Whatever else history may say of our mid-20th century, it will not be able to deny its vigor and vitality, a vigor finding its expression in 100 different ways, whether in our serious affairs or in our speed-crazy sports, in our pursuits of pleasure or in the garish glitter of our cities. But vigor shows itself no more in these than in the astounding growth of our technology. On every hand, there are the unmistakable signs of the arts and crafts of technological man. The testimony of the machine, and of the new man-made of steel, and of automatic processes. The fact of power harnessed to meet man's growing needs. And with him, driving his machines, succoring his brain children, sustaining his vitality, the lifeblood of the scientific age is steam. Of steam, it has been said that it's industry's most wonderful, flexible, adaptable tool. Once its ways are known, it never slips, never breaks, and never blunts its edge. So surely we should pause to learn something of this versatile fluid. It is superheated steam in vast quantities which is used to generate electricity. We should now consider how the steam is made. This laboratory method was the basis of the early boilers, like this haystack boiler, where the fire is below a large mass of water. Better steaming conditions were produced by this fire tube boiler, where the fire was in a tube inside the drum and was surrounded by the water. Better still was the introduction of two fire tubes in the famous Lancashire boiler. This and other fire tube boilers have been developed into excellent units for the smaller duties and are still very widely used. At a later stage, the so-called water tube boiler was introduced. And as its development for large capacities and higher pressures has been so rapid, we will give it some attention. It depends on the promotion of good circulation of the water. Suppose we have water in a vessel here. And suppose we have a tube connected to it like this. Now we heat one leg of the tube, being careful to screen the other leg from the heat. The water in the heated side warms up and expands, getting lighter in the process. Being lighter, it rises up the tube, allowing colder, heavier water to take its place. This in turn is heated and rises, and very soon a circulation of water builds up. In time, some of the water in the heated leg turns into steam and will collect above the water surface. From there it can be taken for use, the water being recirculated through the tube. This is in fact a recirculation system. So long as the two legs of the tube are heated at different rates, the column of water and steam in the more highly heated leg will be lighter than the other, and circulation will continue. This is called natural circulation. In practice, the heated leg, or riser, is in the furnace, and the other leg, or downcomer, is often outside. Downcomers may also be inside the furnace, but if so, they will be shielded from the greatest heat in order to maintain the conditions for circulation. In our case, we will keep the downcomer outside. Also in practice, the water vessel is a large closed metal tube called a drum, and our single riser becomes many tubes. Similarly with the downcomer. In the huge modern installations, the risers become hundreds of tubes, completely covering all four walls of the combustion chamber, and rising up to a height of over 100 feet. Some of the water circulating through the heated risers is converted into steam. At the same time, the water rapidly flushes the steam from the tube metal, and so prevents the tube from overheating and bursting. The hot gases leave the furnace through a gas pass, To save wasting the heat still in these gases, they're usually sent through an economizer. Here, the feed water is warmed up by the hot gases before it ever gets into the drum. Here, on a most accurate model of such an installation, we can see the features we've talked about. At the top, the drum, from which the feed water enters the boiler and where the steam collects after circulation through the boiler tubes. The downcomers outside, dropping down the full 100 feet and more of the combustion chamber, eventually to join headers running across the bottom. Inside, the risers, covering the walls of the combustion chamber. In fact, arranged like this, the risers form water walls, hundreds of closely set tubes, often with fins welded down each side to increase the heat they absorb. It's here, in the risers, that the steam is made, in these tubes, exposed as they are to the radiant heat of the furnace. Finally, the risers return to the drum. The economizer is on the right. Here, the water is heated before entering the drum. And that, in bold outline, is the monster modern steam generator. You get an idea of its great size when you realize that the toy man is on the same scale as the model. But there's much more to it than the general outline we've seen. Take the water itself, for example. Elaborate water treatment plant is necessary to make sure that the water entering the drum is chemically suitable and safe for the system. Inside the drum itself are a variety of devices for separating the water and steam, since dryness of the steam is fundamentally important. The latest method of separation is by cyclone separators. The steam-water mixture enters at the bottom. The vanes cause it to whirl round rapidly. Since the water is heavier than the steam, it's thrown to the edges. It's then deflected over the edges, finally falling back for recirculation. Meanwhile, the steam passes on up and through scrubbers on top, where further water particles are thrown out. The steam leaving the drum is now dry, saturated steam, and is ready for superheating before being passed to the turbine. For superheating, the steam leaves the drum at the top, crosses the combustion chamber, and enters the superheaters. These are the superheaters. They're placed at the top of the chamber and in the gas pass. The dry steam flows through the superheater tubes, where hot gases from the furnace give up heat to the steam and so superheat it. We've now seen something of how superheated steam is produced in one of the larger modern installations. And it's worth noticing how the practice of steam raising has advanced since the early days of steam generation. In the early 1920s, a big boiler would produce about 40,000 pounds of steam per hour at about 250 pounds per square inch pressure and round about 600 degrees Fahrenheit. Nowadays, one big boiler is designed to make as much steam as 35 of these earlier boilers. That means 1,400,000 pounds of steam per hour, and it's at nearly 10 times the pressure, 2,450 pounds per square inch, and at getting on for twice the temperature, 1,060 degrees Fahrenheit. In addition, 1,250,000 pounds of steam per hour are reheated, but we'll consider that later. Comparing the 1920s with the present day is like comparing a new baby with a heavyweight boxer, or a prefab with a festival hall. Monster steam generators of this type were designed for the power station at High Marnham, here seen as an architect's impression. The actual work of building the station began here, beside the River Trent. With plenty of water available and a ready-made supply line, this was an ideal site on which to start the task of building this huge station. But before even the first excavations became possible, a very great deal of new thinking had been necessary. High Marnham was designed to work at 2,450 pounds per square inch, whereas the most we had to deal with before that in this country was 1,600 pounds per square inch. This pressure of 2,450 pounds per square inch is the pressure that would be felt at the foot of a column of water nearly a mile high. It's more than a ton on every square inch. Or looked at another way, it's the pressure that would assail you if you went to the bottom in nearly 5,000 feet of water. And that's the pressure that the steam generators at High Marnham have to withstand. And it raises some interesting design problems. You'll remember when we talked about circulation, we said that so long as the water or water-steam mixture in the heated side was sufficiently lighter than the water in the other side, natural circulation would result. At 1,600 psi, there's still ample difference in density between the two sides for circulation to be satisfactorily maintained. But at very high pressures, the difference in density is nothing like so great, and the circulation becomes less satisfactory. With the attendant risk of overheating and consequent deformation of the tubes. In fact, it's desirable now to assist the circulation by means of a pump in the circuit, which would have the added advantage of bringing circulation under control. At High Marnham, when planning the steam generators, the designers elected to have assisted circulation. For this purpose, they placed the pumps at the foot of the downcomers, here. Since circulation can now be controlled to suit the boiler design, rather than the boiler design to suit circulation, the best layout of drums, tubes, and other components is possible. Another advantage of assisted circulation is that smaller bore tubes may be used. Comparing them with a larger bore tube essential for natural circulation, we see that they're thinner and lighter. Further, they operate under less stress. So, assisted circulation is one of the features of High Marnham. Another is the arrangement adopted for reheat. Without reheat, as we know, steam goes from the steam generator to the turbine. It does its work and is then condensed to water in the condenser and returns to the steam generator to be reconverted to high-energy steam. The efficiency of this cycle can be improved if, after the steam has expanded through part of the turbine, it is returned to the steam generator and heated up again before passing through the rest of the turbine. This is a reheat cycle, the steam being reheated after doing part of its work. For High Marnham, a reheat cycle was adopted. When we look at the steam generator from this standpoint, we see huge twin combustion chambers. Fed from a common long drum, two nearly identical furnaces stand side by side. The furnaces have identical water walls, through which the steam-water mixture rises to the common drum. After separation in the drum, dry saturated steam goes to two primary superheaters, one for each furnace. The steam now goes to a single secondary superheater in the right-hand furnace exit, where it's brought to the full working temperature. It's now at 2,450 psi and 1,060 degrees Fahrenheit, and is ready for the turbine, where it goes to do part of its work, dropping its pressure to little more than 500 psi in the process. Most of the steam is then brought back to the reheater, which occupies the same position in the left-hand furnace as the secondary superheater in the right-hand furnace. Here the steam is heated to 1,005 degrees Fahrenheit, though its pressure stays round about 500 psi. It can now return to the turbine and finish its job. In this way, 1,250,000 pounds of steam are reheated per hour. So with reheated steam, the generator delivers over 2.5 million pounds of steam to the turbines every hour. But High Marnham is not the end of the story. It's only a recent chapter. Already on the drawing boards are units with nearly 3 times the capacity of High Marnham. 3,900,000 pounds of steam per hour. And capacity is not all that will increase. Pressures will rise into the supercritical region, even up to 5,000 pounds per square inch, and perhaps beyond, and temperatures up to 1,200 degrees Fahrenheit. These call for radical changes in boiler design. We've seen already that there's much to recommend using a pump to assist circulation. But at and above critical pressure, not only is forced circulation essential, but as steam and water do not exist as separate phases, they cannot be separated in a drum, so that recirculation of the water is not possible, and a drum serves no useful purpose. Instead, feed water must be pumped directly into the furnace tubes, where it will pass through continuous tubing until it's all converted to steam before emerging at the steam outlet. Such a system is called a supercritical once-through forced circulation boiler, and is undoubtedly one of the steam generators of tomorrow. A tomorrow whose promise must surely be brighter for the continuing vitality of our engineers and technologists, bringing to mankind the necessities and luxuries of this and any other modern era.